So now we'll take a quick look at code injection. Right, is everyone at this point? So code injection is sticking code somewhere that it's not supposed to be. So the first part that we'll look at is XSS. That will describe it fairly well. So you'll see on that first page there's a URL, right? So you can go to that URL. You can copy and paste it into your browser. And we should get a nice page like this. Very simple, right? We see a basic header and a basic form, right? So we're going to go ahead and enter some text. And we submit that, and it's going to show this text in quotation marks here. Right? Very simple. It just echoes it back. This is like, say, if we search for something in Google. Google says you searched for this, and then gives you the results, right? So we can see that in a lot of different pages. What we can also do, if we look at our page, if we look at our page source, so view page source, right, we can see that it's just quotation mark and exactly what we entered, and then text. So we can go ahead and make text bold. Right, so we enter this HTML into the search bar. Can everyone see that okay? I'll make it bigger. So we make that text bold, and then hit submit. And now I forgot the slash here, so it's keeping the whole thing bold, right? But that HTML is now affecting the page that it's supposed to just be outputting the text we entered to. Kind of cool, eh? Right? So we can enter whatever we want. We can enter image tags, etc., etc. There's one thing that's particularly powerful and particularly dangerous that we can enter. So I'm going to do it up here in the queue, just because it's easier to do it straight from the URL. We can enter a script tag. A script tag runs JavaScript on the server, or on the browser, sorry. Right? So script, and I'm going to change text to alert, say 2. And reload that, and the page now gives me this pop-up box that says 2. That was a script we ran on the page that did that, the alert function. Right? You don't all have to get that to work. I'm just sort of demonstrating it. You can play around with it yourself. These scripts can do something even more dangerous. Let's take a look at our source again. View page source. And we see here we have our head. Its ID is head1. We can change that. So inside the script, I'm going to type some stuff. You don't have to follow along. Just watch what it does. Document. That gets the document dot get element, capital element, by capital, ID capital, and then in brackets and in quotations, head1. That gets the head1 element. Dot inner HTML, that's going to change the HTML inside of it, equals, and then in quotation marks, I'm going to say like deep rocks. And then we'll stick a semicolon at the end. Hopefully this will work. And there we go. That script runs on that page, and it changes the page as it's running, right? So it changes the page on the fly on the client side. So if your site is vulnerable to XSS, you can enter the right thing into the URL bar and get your site, it's still that domain name, to change itself. Right? So remember how phishing, you could look to see if the HTTPS was on, right? So for like Facebook, we've got that little green lock icon here, if it wants to come up, right here. That's still going to show with XSS, because this is all on the client side. It's still getting the data from Facebook, but the script runs on our browser. It's also going to be the Facebook URL, but it's running on our browser. It's going to change the site. So we can actually, instead of changing the text, we can go ahead and change the action page of a form. And in changing that action page, we can do like phishing, only on the actual site. Right? So XSS is a very dangerous thing, and if you click a link that someone emails to you, it might be the legitimate site, it might not be a phishing site, but it could be to a URL that will use XSS. It will insert malicious code into the website and cause that website to change itself and show something the website was not meant to. Questions on that? Right, so you guys can play around with that page, and you can do that now, and we'll move on as well. How do we protect against XSS? Certificates don't work, right? We're getting the data from the site. So we can be vigilant, right? Look at our URL. See if you can see what looks like an XSS injection attempt inside that site. If you see a long URL, take extra care to take a look through it. See, is that a script that's making it so long? And if so, you probably don't want to use it. The most important is sanitizing input. That's something that's done on the server. So I'll show you the server code. Oops, go back a bit. I'll show you the server code that is running this try XSS. I think it might be in your shared folder. Do you see a try XSS in here? No. Okay, I'll show it to you on the server. So what we see here, we see this checking if the no BB is set. We'll look at that in a minute. But if it's not, then we're going to send this HTTP header. This sets XSS protection in the browser to be false. If we don't do that, the browser is actually smart enough to catch this. If it sees this script in the URL and sees it being echoed out in the page, it's going to take that script out, right? So if we set no BB to anything, so I'm just going to go and, so if you want to include multiple arguments in the get line, we can do question mark something equals something and no BB equals true. I'm going to go there and this, yeah, there we go. And now the browser has stripped out that script, right? Because it's not sending this HTTP header that says not to protect from XSS. And so it's going to strip out that script. We can look at the source. And we see where that quotation mark should be. We still see the script, but the browser is not going to run it, right? So that is XSS protection. Most modern browsers are smart enough to protect against that, but it is not foolproof. If you have a user using an older browser, it is still susceptible to XSS. Furthermore, if you save this in a database somewhere, and then it gets it from that database and sends it back to the user, the browser cannot tell that it came from a database that came from injected scripts. So XSS protection will not work there. So browsers are getting smarter, and by using a modern browser, we can protect against URL-based XSS, but it will not always work. Questions on that? Right, and we can see that all the rest of it does is just insert the code that we entered into our queue, right? So we insert that queue, right? Fairly straightforward. So sanitizing input is what's most important. If we just strip out all of those opening brackets and closing angle brackets, that script tag will no longer be a script. If we strip out quotation marks, we can't actually include any gut element by ID. We can't actually put anything in the inner HTML. That effectively renders our scripts useless. Watch out, you also have to strip out those little angle quotation marks you see on top of the squiggly on the keyboard, because some older browsers use those as quotation marks as well. So by sanitizing our input and removing a couple characters that are illegal, we can prevent XSS from working. That is by far the most effective way, and there is, to my knowledge, no way to circumvent that. Questions? Another type of code injection is SQL injection. SQL stands for Structured Query Language. It is used for getting a database entry. And we send it a little bit of code that says, say, get all from table deep students whose name is Kelvin, and it'll get Kelvin's record, right? And then after that, we have an ending quotation mark to say that, okay, we're done with the name Kelvin. If we include in the name Kelvin an ending quotation mark itself, it'll finish with Kelvin, then we can include other SQL code beyond that. So here's another XKCD comic. You can take a read through it, right? So we see this end quotation mark. Drop table students is going to delete the entire table, right? So the joke is this mother names her son with these characters. They enter it into the school's database. It runs an SQL injection attack and deletes all the students. Kind of clever, eh? Questions? Okay, so the last one we'll look at, oh yes. Pardon? Yeah, so drop table is SQL code for delete that table. Another last one we'll look at for code injection is buffer overflows. Oops, yeah, back. Is buffer overflows and running data as code. So open up your shared folders, and we'll open Xs again. Right, and again we want to get our compiler and our emulator. Okay, so we have a basic program right here. It doesn't actually do any pushing or pulling. What we're going to do is we'll add to this program move. SP stands for stack pointer. And then we'll say put 20, see if that works. And then we're going to push the value, actually it's just PSH. We're going to PSH, so push the value, say 2342. You can put whatever you want there. Right, and that's going to assemble in front of us. We're going to load that into the emulator. So that loads a fairly simple, and change .stackFF to .stack100. Right, that'll load some stack space below us. So now we have this program right here, right? 20 is decimal 20. It's going to be a little bit smaller. It's up here. So we'll change that to something larger, say 50. And then load that. So now what happens is we set the stack to 50. 50 is right where our executable code is. When we push that number to the stack, it's going to push that number onto a stack that's where our code is. It's going to change our code. So let's try it out. We're going to load that and step. So we're going to set SP to 50. And now, actually, so SP 50, that's 32. And 32 goes right here. Okay, that's kind of interesting. So let's make it 51 so it isn't quite 51 or 52, so it isn't quite as nicely alarmed. So that's going to compile. We're going to load that. It'll change it slightly. Step. And so that's going to be 52, which is 34. Right, 34 now starts here. So that's going to actually change the code. Step. And then we're going to push this number to 34. Our 30 is here. Our 4 starts here. Step. It now changes the memory that just pushed it. We've now changed the executable code. So we're going to step on, and does it jump start? So it does jump start at some point. Okay, if it did, then it would have. It didn't jump start in this case. So we're going to change JIE to just JMP, so it will always jump. And now we're going to load it again and run through. So move, inc, add, compare. We don't do that. Now we're going to jump. Actually, we don't even want the start. No, we don't want start. We want main. And we'll put start up at the top. So what I'm doing is start was kind of in the middle. We want to go to the very start of the program. So I'm going to change start and put it right above this first move, start colon. So jump start. Right? If you're following along, that's awesome. If you're not, you can just look up on the screen. So now it should work, right? So now we're going to jump to the beginning, but we've changed that beginning code. So we're going to load it again. Step, set SP to 34. Step, push this, look at this. This is going to change when we push it to the stack. It now changes that code. We're going to move along until we jump, and now we jump up. And this is jumping up to somewhere where we've changed the code. And now we get an error because we didn't change it to anything useful. Sorry? So what we did is our stack is a piece of memory, right? When we push something to the stack, it changes that piece of memory. we are pushing it to, or we're setting the stack to be where our executable code is in memory. So when we push a number to the stack, it's pushing that number to where the code is. It jumps up to the start. So it's now jumping up to where that code was that we've overwritten with this data that, or 2342. It's now trying to evaluate the binary form of 2342. It doesn't know how to evaluate that, so we get these errors. If we were smart about it, we could put the right number so that that number in binary corresponded to actual executable code, right? And then we could make it do whatever we wanted by pushing that to the stack. Everyone following so far? Right? You get the general idea of how code injection works. So a buffer overflow works in a similar manner, except we say this part of memory is going to be for data, this part is going to be for code. If we make the data longer than the part we've allocated for it and we don't check for that, it will overflow from the data section into the code section. So by entering a lot of data and then specially designed data that is executable code, we can actually make a program do what we want just by entering the right long piece of data into it. Questions on that? Right, so that's code injection.